you don't do science to become famous. You do science because you're engaged. You want to understand what's going on at a basic level. You want to understand what's going on. If you can do something that's useful, great. But that's not really the primary motivation of the type of science that leads to discovery. I mean, that's basically curiosity-driven research.
This is a conversation with Australian immunologist Peter Doherty. Peter's famous for his breakthrough research on killer T cells, and he's more accomplished than I can really do justice to here. Suffice it to say, he's an Australian of the Year recipient, he won a Nobel Prize, and we filmed this interview in a very large building named after him. He's also an accomplished author and brings over 50 years of experience in science to the conversation. We discuss immunology, science and politics, and existential risks. I'm Shane Farnsworth, and this is the Escape Sapiens podcast. If you enjoy these conversations and want to help support me, the best way you can do so is by liking, sharing, and subscribing. And now, I'm pleased to bring you Peter Doherty. I hope you enjoy.
Escape Sapiens.
So you've got a Citroen t-shirt.
Yeah. You a car person or?
I used to be more interested in them than I am, but...
All right, that's me testing.
We were just talking the other day about the virtues of a car which you could jack up on its gas. That car, you could jack it up so that you could drive it across a paddock full of stumps.
Right.
It had a hydraulic lift on it.
You lived on a farm?
No, but I trained as a vet. That's my basic training, is in veterinary science. So.
Mm-hmm. So you're often dealing with large animals. Why did you decide to transfer across?
I was going to save the world by producing more food. This is back in the 1960s, 50s and 60s. And so that's what I was going to do. I didn't want to be a doctor because I didn't want to sit in a doctor's office listening to people whine. And that was a decision made as a boy at the age of 16.
And cows can't complain.
When I was, totally zero empathy. And, basically, it was a different time,
But if you had no empathy, why did you want to save the world?
Oh, Methodism. I was brought up in Methodism, which is, a sort of a service type of Christianity, basically. The Methodists hived off from the Low Church of England to basically stop people drinking themselves to death and ruining their lives. So if you're a Methodist, you didn't drink and you didn't dance. Yeah, that was basically...
But so it wasn't ego?
It probably was, but who knows? No, it wasn't. It wasn't really. I had no thought of winning Nobel Prizes or any of that. I mean, you wouldn't become a vet. I'm the only vet to have ever won a Nobel Prize.
Really?
Yeah.
There's obviously then no Nobel Prize in veterinary medicine or anything along those
lines? No. There's no Nobel Prize in mathematics. There's no Nobel Prize in lots of things. No Nobel Prize for geologists. Sometimes they can work them into, climate change, obviously. It's physics, chemistry, medicine in the sciences. Then they added the Swedish Banks Prize for economics in the 1960s. The banks bought their way into the Nobel Prize, which made the Nobel Prize worth a lot more money. But it's treated as a science, it's the dismal science, economics.
So before we started, we were talking about Fauci. And the sort of attacks you get on Twitter.
I've known Tony a long time. He's a very smart guy. Pretty good scientist and a good doctor, I think, and generally committed human being to try and make things better. He's been running National Institutes of Allergy and Infectious Diseases, I think, since the 1980s. He's worked with multiple presidents, including Republican presidents, got along very well with them until Trump came along. And he's just very effective and at getting things done.
Why do you think he became so attacked? I mean, you see...
Well, he was standing up there and if not contradicting Trump, correcting him. And there are a whole lot of people who thought Trump was God. And, we just thought he was a a con man and a liar, which he is. And but Fauci was required to deal with this guy as President of the United States. I don't know how he stood it, but basically he did. Though he backed off latterly, and his offsider was handling a lot of it.
Do you think that politics has become way more divisive today? I mean, I can interview you also as an octogenarian, and
politics is very polarized. I think, and I'm for various reasons, but it's also the idea that the media has also become very polarized, and the idea of a media organization. I mean, some media organizations are simply now propaganda organizations for a particular political view, and they're toxic. And Trump constantly disparaged the legitimate media. I mean, papers like New York Times, Washington Post, National Public Radio in the United States, and so forth. That was fake news. Actually, The Knowledge Wars, the book that I wrote in 2015. I didn't use the term fake news. I used invented constructs, but it's basically fake news. And basically, there's a very good little book on it by a man called Harry Frankfurter, and I think he's a Harvard philosopher, and it's called On Bullshit. And basically, that's what Trump is. He's about bullshit. And Frankfurter makes the point that bullshit is actually worse than lies.
Why?
Because bullshit seduces you into a particular view. A lie doesn't necessarily do that. And you may tell a lie because you don't want to hurt someone's feelings or various things. But bullshit is deliberately a seductive act.
Do you think, so Trump mentioned various proposed cures that were in the media at various points. Do you think because he was a proponent of them, they were shut down?
No, he has a massive ego, and he's totally narcissistic, and basically he was providing the solution that the experts couldn't provide. And so we had hydroxychloroquine and so forth, which wasn't an unreasonable idea at the beginning, considering its mode of action, but really all the clinical trials were done, it was shown not to do anything useful. And so he was providing the solution, the great Trump. And he did, and I think Fauci obviously pushed him to this, he did set up Operation Warp Speed to develop vaccines fast, and that was good. And I think it's interesting that a lot of the people who are pro-Trump sort of ignore that fact that it was Trump who really pushed this forward by providing the funding for it. So I think it was just a very difficult interaction. And Trump is a totally, and we've never seen a politician quite like that, not at that level.
What about, so people are also fairly divided when it comes to anti-science. So for example, you might see on conservative sides people who are who question climate change, whereas on the left you might see people who are anti-GMO.
I think I think the word conservative has been hijacked, quite frankly. I think the Republican Party, you could say, was the conservative side of American politics for a very long time. But with regard to science, the Republicans were often the best supporters of science, because what they saw was that it earns money, and it does the job that right-wing politicians do in the United States. They take public money and they transfer it to their friends, and a lot of their friends are running companies that are science. Pharmaceutical companies are their friends. The people who are making the stuff the scientists buy are their friends. I mean, because they're business, it's big business. And also they were intelligent, and they saw that innovation is really the United States' great strength. And even when Trump became president, Trump tried twice to cut the budget of the National Science Foundation and the National Institutes of Health, which are the two big government budgets that work through competitive peer review. And both times the Republican Congress turned it back. And the reason they turned it back is they know that this earns money. If you look at Silicon Valley, there's massive wealth transfer from the public to the private sector at that level. If you look at Silicon Valley, it was largely funded by Department of Defense and Department of Energy contracts. And so, they're smart enough to or they have been, I'm not sure about the current Republican group, but they're smart enough to recognize that this is a source of America's prosperity and dominance globally. And basically, if they give that up, they're really, they don't have anything. because the Chinese can produce stuff much faster and much cheaper. Quite frankly, they've given up a lot of that manufacturing because Americans made money out of it. That's why it was done. I mean, they threw all their workers under the bus, and we love globalization. We're the good guys, but basically they threw their own workers under the bus, and they're very angry. But they identify a lot of those people identify the reason wrongly, and they don't identify the people who actually did it. A lot of those people who run big industries who transferred them to China, they don't vote Democrat.
Right, and so, as an advisor, as a scientist, what do you think your role is then in politics? Do you think scientists should take a more active role?
I think scientists need to be involved in public communication as best they can. I think we all should be. You can certainly talk to politicians. The problem, though, is you can become captured by the political process. Mm-hmm. And so I think for those who have those abilities, and Tony Fauci is one, to negotiate that process and do it do it well, and that requires I think a certain type of mind and a certain type of set of skills. I think it's great they're involved. I mean, if they don't get involved, I mean, in the past, particularly the Republican Party in the United States had some some terrific champions for science in the Congress, and the thing was that when I first went to the United States, which is in the 1970s, I was impressed by how well they worked across the aisle, because the committees are all bipartisan. So you've got Ways and Means and so forth. They've all got Democrats and Republicans on them, but the chairmanship of the committee switches to the majority party in the House, and so basically, I thought that worked extremely well. And then when you saw C-SPAN, which televises a lot of, a public television channel, which actually broadcasts quite a number of committee hearings, or used to, then you would see that these people were actually working together. So there's the theatre of politics. But now it's all, the theatre has taken over. And so I don't think of what many people describe as conservative politics as conservative. I think of it as reactionary or regressive politics.
But do you think the theatre has really actually taken over, or it's just that it's more present in our lives because we're connected on social media and so on?
Considering some of the people who are being elected to the Congress, yes, the theatre is much stronger, because a lot of these are people of no substance. And you can see that. I mean, they're crazy. I mean, they buy into these QAnon theories. The QAnon, as far as I'm concerned, it's the, have you heard of the Protocols of the Elders of Zion?
No.
This was a document that was circulated by the Nazis.
Okay.
And a lot of the things that are attributed to the deep state are actually just taken straight from the Protocols of the Elders of Zion. It was anti-Semitic, obviously. The deep state thing is not necessarily anti-Semitic, it's anti-government, but that's where it comes from. I mean, it's the same wording, almost. And it was done by some crazy guy, and all these crazy people have found a home there.
When it comes to conspiracy, when it comes to people who are pushing things that are anti-science, what are the limits to debate? Like, for example, should you jump in the trench to fight against flat Earth? No,
I mean, there's no point in trying to fight against flat Earth. I mean, the people who are convinced of flat Earth are not going to be convinced of anything. A lot of the anti-vaccine thing it was at least it was a diversity of people. People who've had a bad experience with a vaccine. Any medical procedure is a risk. There's a risk factor to it. And some people have sometimes had bad experiences, or their kids have had bad experiences, or it can be just the kids whining and whinging after the vaccine dose. It could be that they say, I will determine what happens to my child, government will not do it, and all this sort of thing. So there's all sorts of different levels of thinking. But a lot of it's become linked up now with conspiracy theories. And one of the things, for instance, that we've seen in the anti-vaccine thing with COVID vaccines, which were a novel technology. It had been around for quite a while, but never rolled out as a major vaccine initiative. Firstly, enormous amounts of disinformation, but also, there is some risk. and some people, and it was particularly some of the risks were certainly not predicted. The myocarditis thing with younger males, and there's a risk-benefit equation. It's not, to my mind, that clear what that risk-benefit equation is currently, because the vaccines are not very well matched to the virus. So there's a lot of subtlety to it, but there's no subtlety to this position, and it's sort of consolidated a lot of that sort of attitude, and then of course the internet reinforces all these things, and people find each other, and these conspiracy theories build on themselves.
What do you mean when you say that the vaccine is not well matched to the virus?
Oh, well, the virus has been changing. I mean, the vaccine, there is an Omicron variant in the vaccine that's used here, the newer vaccine here, which hasn't really been used very much here, and in the United States. The American one has the original Wuhan strain virus, and the virus and no longer makes antibodies that neutralize the virus, plus another product against Omicron BA5. Now we've moved on past BA5 already, but and the Australian vaccine that we have here at the moment is a Moderna vaccine, which has an Omicron BA1 variant. So I'm not really sure what those vaccines are doing, and they're not well matched to current strains. Now that matching matters a lot with the antibody responses, which is what stops transmission. So they're not stopping transmission much at all, I think, whereas the last virus they stopped transmission fairly effectively with was the Delta strain. But they do seem to be keeping people out of hospital, and that may be the T-cell response, part of the response that I studied, which is not under such strong selective pressure. And because the actual bits of the virus that are seen by the immune system with that response often come from very conserved proteins like proteases, which have a function. And it's not that easy to change a protein structure if it has a function that actually does something within the cell. Whereas the function of the spike protein is simply to bind to the receptor on the cell to get it into the cell. And there seems to be a number of ways that spike can be changed and still work. And so this virus has changed much more than we expected.
I'll get into your research and immunity in a little bit, but I just wanted to push down this direction a little bit further. What's your view when it comes to forcing people to have the vaccine? So, for example, children have to have the vaccine.
I'm generally not a great fan of vaccine mandates. I think if, and most of the medical profession is not actually a great fan because of the sort of things that have happened. I mean, it's certainly the case that the vaccine mandates that were brought in did cause people to get vaccinated when they probably wouldn't have, and that was probably useful at reducing transmission up to about the Delta phase. But I'm not sure it's been much use to reduce transmission since then. What it has been useful for, I think, is to still keep people out of hospital, which is important because there's been a tremendous pressure on our medical system. So, but vaccine mandates, I think you have to be very careful in mandating this sort of thing.
Do they lower also the incidence of long COVID?
It's marginal. It was working, and again, with the earlier strains where it was giving more protection, I think, I tried reviewing the literature on it. It's a very complicated literature for all sorts of reasons, partly because a lot of it is self-reporting, and partly because no one has gone into long COVID, and I think there are several different types of things happening. I mean, for instance, people are very sick with COVID, or very sick with flu, and they go on a ventilator in an ICU. There's a phenomenon called post-ICU syndrome, PICS. So I think some of the things that we're seeing, where there's just damage is done and it's damage that can't be repaired. And so I think with some of what we're seeing with long COVID is PICS. But then there's the other phenomenon where people they get sick, but not all that sick. They don't go to hospital, but then they have this long debility. Now that's the long COVID, but a lot of the long COVID data doesn't distinguish between those two, and I think they're different, and the mechanisms are probably different. So I think firstly there's the fact that there's no good classification of it into different types, and then the other factor though with it is that a lot of long COVID is self-reported, and when you get into self-reporting, you do get into various complexities that are difficult to really analyse. But overall, early on, from the Americans don't have a public health system the way we do, or the British. The British National Health System, for instance, was giving very good data on what was happening because they command all the hospitals in the UK, and they bring them all in as research hospitals. We can't do that because we've got all these different states, and it's hopeless actually. The Australian system is very siloed on the basis of federal, state, all sorts of things, which makes things like that very difficult. We do some things very well, but not that. But the Americans have a massive public health system called the Veterans Administration. The Veterans Administration treats for life. They look after the health care for any permanent member of the Army, Navy, Air Force, Coast Guard, the United States Public Health Service Commission Corps. These guys, these doctors, many of whom I knew as researchers at Bethesda or in Colorado or somewhere as full-time researchers, and you'd normally walk in and see them dressed in blue jeans. They were required to wear, under one of these Surgeon Generals, were required to wear a uniform every week, once a week. And so you walk in to see this guy who you usually see in blue jeans and sneakers or shorts, and he's dressed like an admiral. Really, looks like a naval uniform. And the other one is the National Oceanographic and Atmospheric, the NOAA, the Weather Service. They're also a commissioned corps of the United States.
So they have very good
healthcare. They have very good healthcare, and they have very good data. But it's heavily skewed towards males and of course older people.
Right.
But it's a very good data set actually, and some of their data has been very good on long COVID. At the moment, I think vaccination may be protecting you 15%, 20%. It's not clear, but it's not giving you great protection. But Omicron, I think, is probably causing less long COVID, but I'm not sure about that either. I've been taking time out from it a bit, and I'm going to go back to it later in the year, and I may write another book about this whole. I've already published that Insider's Plague Year book, and I've been writing these online pieces. But I may write another book about, where are we with this, or the challenges facing us, because I think the way we've responded to COVID actually gives us a lot of insight into the limitations of our response in things like climate change. Yeah. And I've been writing about that. This book is partly about that.
Now that the dust has settled, I mean, you're not sure where the future is going to go, but now that the dust has settled a little bit, which countries do you think actually did a good job? I think
we really should look at that very carefully and do it very thoroughly. I think academics should do it because they go in depth, or people who are in the foundations or operations that go in depth and do analysis, and it should be free of any political influence or any bias. And so we should look at the sociology, we should look at the mental health consequences, we should look at what different states did, because different states did different experiments. I mean, Sweden did one sort of experiment by staying open. We shut down a lot, but then we opened up. The different American states did different experiments. The Washington state, for instance, was not that different from what was done here. It was, they did a lot of lockdowns and all the rest of it, whereas Florida and Texas did things completely differently. So I think we really should look at what was justified and what worked, if we can actually work it out. I think we could probably come to some good conclusions, but I'd like people who are really intellectually strong and working in their disciplines to actually give us those sorts of insights. Whether that'll happen, whether anyone will fund it is another matter. But I think probably some of the response here was a bit over the top. We were very scared. Firstly, everyone was scared because we had no vaccine. It was a new infection. It was killing people. And I think everyone made the mistake of thinking, oh, well, we get a vaccine, we'll be okay. But of course that hasn't really happened. And I thought all along we should have been pushing much harder for drugs, because I know that the drugs would work and much less likely to be subverted. And that's the AIDS experience, actually. And so I think the scientific community didn't get it all right by any means. Public health community didn't get it all right. I think what the previous government did was pretty good in the context that it was doing it. Our institute has no role in the public health thing at all. We're just a laboratory. We did the diagnostics for them and the genomics, and some of our epidemiologists were contracted to do models and so forth. But the real decisions about all this stuff are made in the public health community, which in Australia is state and federal. There are different state and federal administrations in it.
You said before that you think that the current vaccines are something like 15% effective.
Against long COVID.
Against long COVID. Oh, yeah. So not in terms of...
No, it's hard to know what the efficacy of them is at the moment, and they're certainly not very effective at stopping transmission. But there's data, and there's also the doctors themselves say they're still confident they're keeping people out, tending to keep people out of hospital if people get boosted up. Yeah.
So what have we learnt then? If you could, condense 3 years of knowledge into...
Well, we've learnt something that I already knew. That is the limitations of our technology. We talk about medical technology. We talk about all technology as though we can solve everything by technology. But the example I use from climate change is, when did we last make it rain or stop raining? Okay. So this perception that everything can be solved technologically is simply an illusion. It's arrogance. I mean, we should try to solve these problems technologically. Climate change, we should try to solve it technologically. COVID and all the rest of it. But the perception that we can solve all these things is just an oversell. And, people die.
Right.
I mean, if medicine could solve all the problems, people wouldn't die. Of course, that would create another enormous problem.
So let me jump to your work then, and work maybe back in this direction towards the end. But I want to know, what is it that makes you most excited about working in immunology? What is that beautiful aspect that makes you interested in the field?
Well, I got interested very early on. I trained as a vet, but I was in the lab fairly early after graduation, and I was working on trying to understand infectious diseases, initially of domestic animals, and then that switched into basic medical research, which means I moved from being a sheep doctor to being a mouse doctor, an MD, and so I've been trying to understand disease mechanisms and how the immune system works to handle infectious disease. And as you can imagine, that is very complex. And there are things, when I started out, everyone talks about cytokines and chemokines and interferons. None of these things we knew. We didn't know they existed. I mean, there's been an enormous period of discovery over the last 50 years, particularly with molecular medicine. So what I've seen as I've tried to understand what an infection is, how it works, how it kills us, how we stop it killing us, and all the rest of it, how it debilitates, that has become inherently infinitely more complex as time went by, as we've discovered more and more mechanisms that are operating. And we will, I think, after one of the things that will happen after COVID is there's been some very, very good science done, but it's still being done. A lot of it's not published yet. We'll get a lot more insight into these issues, but we may not necessarily have solutions as a result of that insight.
One of the things I'm really curious about is how the body stores information outside of DNA. And so when it comes to immune response, what I want to know is, what's the difference between someone who is immune to a virus and someone who's not? Where is the information stored?
It's basically stored in cells. I mean, it's in the brain you have a central processing unit, the brain, and basically naively, I mean, the first 5 years of my research career, I was basically working in neuropathology. So, I have some brain stuff And I could have gone that direction rather than the immune direction. But so basically, naively, we think of information being stored as a result of establishing networks, and then trimming those networks. There's all this axonal trimming goes on, so memory gets modified. But we think of it as a kind of hardwired system, right? The immune system is not hardwired at all. It has no central processing unit. So the basic cell, responding cell of the immune system are the lymphocytes, and they have receptors on which are highly specific and enormously diverse. So when you get COVID, there'll be a few lymphocytes, B cells, the ones that make the antibody ultimately, that'll have a receptor for something on that virus. And they will engage, they'll become activated, they'll engage with virus-infected cells, called dendritic cells principally. They'll become activated, and they will multiply. They'll clonally expand. As they clonally expand, they will differentiate. Some of them will become effector cells. For instance, with the antibody-forming cells, they'll become what's called a plasma cell, which is an end-stage cell, which will sit in our bone marrow and pump out antibodies. And some of them will become memory B cells. So memory in the immune system is at the level of individual cells. It's just we've got more of them, and they're in a different differentiating state as a result of epigenetic effects. So basically, there are more of them, they're genetically somewhat different, and they can be recalled to immunity. And the antibody-forming cells will keep on pumping out antibody. The T cells, you have to actually recall them. They're sort of dangerous cells because they kill other cells, and you don't want a lot of them sitting around. So basically, it's the immune system in some ways is much more complex than the brain, and it's harder to research on in some respects because it's a disseminated system. Not only is it at the level of the cell that memory works, these cells are in motion. Some are moving around more than others. Some are sitting. They're moving in and out of tissues. We don't even know how big the immune system is at any stage, because it's very hard to measure what's happening with you can measure the component in blood, but that's only a subcomponent. And so it's a very complex system. Some things we can never really, they have to be modeled basically. That's most modelers are not very interested in actually modeling the immune system in that way, though. It's very interesting.
So if I understand correctly, our body has these cells, I think you said B cells, and they're very diverse.
Yes.
And then certain ones of those cells will match up with a particular virus.
You will say they will have a receptor on their surface, which will actually, within the antibody response, which will actually be equivalent to the receptor that's the antibody molecule itself. So the antibody response, you've got B cells that go to plasma cells, and you've got increased numbers of memory B cells. Some of these are circulating around the body, some of them are sitting in tissues, some of them are sitting in the lymphoid tissue, the lymph nodes, the spleen and stuff. And but their product is the antibody molecule, which circulates in the blood, and it's like it's equivalent to actually a gas attack, if you like. You produce all these molecules, you throw them out into the blood. They will be the ones that grab hold of the virus on first contact and stop it getting into a cell if it's a good match. The polio vaccine, measles vaccine, the viruses don't change much. So, but with COVID, the problem is the virus changes, and so. Then you've got the T cells, which actually interact with modified proteins on the surface of the cell that have been modified by the virus, and they kill the virus-infected cells, for instance. So they sort of clonally expand. You get these killer cells out there, which will stop the infection by killing off the virus-infected cells. Then a lot of those cells die off, the killer T cells, but you get memory T cells that are expanded and differentiated, and they can be recalled more rapidly.
And your Nobel work had to do with this process.
The recognition, basically. We found that you've got graft rejection. I get your kidney. We're very different in what's called our transplant molecules. And there was a whole lot of work done on this from the 30s, actually, in graft rejection, people studying skin graft rejection. We knew there was all these incompatibilities. We knew there was tremendous diversity in the system. What we didn't know was what it was for. What we found is it's for presenting bits of virus to the immune system so that those immune T cells are targeted onto the cell. So the antibody molecules are targeted to the virus, The T cells are targeted to virally modified cells.
I see.
Yeah. So that's what we found, that T cells are targeted to. And we found out what the histocompatibility system is for. Basically, it's not what they gave us the Nobel Prize for, but it's what we did find out. We found out why we have a transplant system.
So
it's a self-monitoring system, actually.
But so the killer T cells that you were working with, they will attach themselves to a cell and kill it.
Yeah, they'll you can see movies of them. They'll see a virus. These cells will come in. They will kind of grope it, and then they'll kill it. And they kill it actually by causing it to commit suicide. They actually activate the cell death pathway. You know, all cells are programmed to commit suicide, and when that goes wrong due to mutation or something, you can end up with cancer. It's one of the cancer mechanisms. So what the killer T cell does, it'll come in and you can see these cells, they'll go onto the virus, and for a while it will sort of all look pretty normal, and they're sort of groping it, if you like, moving over it in a sort of amoeboid sort of way. And then suddenly the cell that's going to be killed will go like that. So it's not that you've just made a hole in the cell membrane, because if you do that, the cell blows up like that. But these cells go like that. And so, that's what we found is the recognition, how that recognition kind of happens.
Is the point that if the cell was to just blow up, then you would be distributing parts of the virus?
Yeah, you could. But so what you actually do is that destroys the cell. But actually, that still releases bits of virus. So a lot of the antibody response is against virus components, and it's completely useless. I mean, if you make antibodies against internal components of the virus, that has no protective effect at all. Unless those antibodies are on the surface, unless those molecules are on the surface of the virus or on the surface of the virus-infected cell, the antibodies you make against them are no use. In fact, that's one of the dangers of virus infections, that some of those antibodies you make will actually be cross-reactive with some of our own proteins. And that's where you get autoimmunity coming in.
So the point is, because you're making a diversity of cells, some of those will trigger on your own tissues.
I mean,
do you have to get rid of those?
The immune system, no, it's hard to get rid of them. In fact, you know, once you've got an autoimmune phenomenon set up, it's almost impossible to get rid of it. In fact, there's a tremendous amount of research done in that area to try to say, you know, how could we turn these cells off? The immune system is balanced. It's balanced between dealing with foreign entities like viruses and bacteria and all the rest of it, and balanced so that it doesn't react against self, but it can be kicked over into reacting against self, and that's what you get with diseases like rheumatic heart disease or rheumatoid arthritis or these things, where you've kicked the immune system over into starting to interact with our own tissues, and you get autoimmunity. Multiple sclerosis is another one.
With autoimmune skin diseases, you often see patches over the body. Is the immune system localized in your body, or why is it that you get patches?
No, I think I'm not quite, I'm not really up in it, but if you're thinking of, for instance, the roughness of the skin with lupus, so I think a lot of this is deposition of antibody-antigen complexes that just don't get cleared. You can get a kidney disease, immune complex disease, where these antigen protein antibody complexes, complex with self or something else, are just accumulating in the kidney tubules and destroying your kidney function. And so, you know, these are terrible conditions, but much more common in women. And of course, long COVID is much worse in women. So there are links there.
Why is that?
Women make stronger immune responses than men on the whole. It's interesting, and maybe it's something to do with trying to protect the fetus. But women are much more susceptible to autoimmune disease in general.
When I picture the action of cells on viruses, a virus is very small compared to a cell in my conception. So can viruses get into tissue or find their ways into parts of your body that, for example, killer T cells cannot access?
No, the killer T cells will go into tissues. If there's something going on in a tissue, and the virus-infected cell or the cells that are in there and responding are producing various chemokines or cytokines, they will signal to immune cells in the blood to stop, to really attach to blood vessel walls and extravasate from blood vessels. The lymphocytes can push through between cells and go into tissues. In fact, the T cells are going in and out of tissues all the time. They're you've got you've got two circulations. You've got the blood,
and lymphatic,
and the heart, but the lymphatic system, which is the drainage of the body. This is all the fluid that's been produced in tissues or has leaked out into tissues. So it drains back through the lymphatics, and there's no pump. I mean, the pump is our muscle activity, and so that and the lymphatics come back in through, so if you inject a vaccine here, if it will go into the intramuscular space and into the lymphatic fluids. Lymphatics, either as free vaccine or in cells called dendritic cells, will pick it up. They will then carry it to the filter stations on the lymph system, which is the regional lymph nodes in your armpit. So your vaccine here, your regional lymph nodes are where the response happens, because those dendritic cells that are carrying bits of the virus get trapped here. And then what happens, they send out signals, chemical signals, that recruit large numbers of lymphocytes into it. So you can see in an immune response, I mean, we did this in mice, obviously, but in germ-free mice or in relatively clean, pretty clean mice, the lymph nodes can get massive very quickly because they suck in the lymphocytes out of the blood. You get what's called a lymphopenia. The numbers of white cells drop, trying to find those rare lymphocytes which will actually react with this particular pathogen. So the response when you get a vaccine goes on here. That's why you can often get a sore arm or a sore armpit and feel crap because it's an immune response. So you're producing all sorts of molecules which are pretty toxic. Some of those molecules, because it's trying to get rid of this invader, some of those molecules will go in the blood to the brain. That's why you feel sleepy or you get a fever, all this sort of thing. So and there may even be neurogenic pathways too, where the nerves themselves are being signaled. That's a much more difficult and complex area, very interesting area, the sort of neuroimmunology. But it's pretty clear that if you've got stuff in the blood, it can be affecting centers in your brain. Yeah. So that's where your immune responses happen. Put tattoo ink in there. If you've got a green tattoo, you'll have green lymph nodes for life.
Really?
Or blue or red, I keep telling to my grandchildren, but they say they're still going to get tattoos. And God knows what it does to you medically. I mean, really, we don't know.
Have you actually, I don't know if you've gone through and done dissections of people or anything like this, but...
No, people have gone through and done
and
dissections.
You can actually see the...
Well, it's a classical experiment that was done in lab mice. I mean, people injected carbon black, which is the black. That's why what a black tattoo was. It was carbon. They injected carbon black into a Indian ink, into a mouse intradermally, and that goes straight to your lymphatics, and the carbon gets trapped in your lymph node, and it sits in cells there for the rest of your life. So, and some of those tattoo inks, you don't know what the hell they are. They can sit there for the rest of your life. So medically, there's some evidence that it can be doing significant damage. And of course, people point out, well, the Maori have always had lots of tattoos and they haven't died. How do you know? Is there a lot of Maori that didn't have tattoos?
Something piqued my attention. You said that the lymphatic system doesn't have a heart, and so it's our movement that sort of pumps.
No, there's no pump. No, yeah, so that's why on a plane your legs swell up.
Right.
It's lymphatic fluid. That's elephantiasis, that terrible thing where the leg...
Yeah.
That's because the filaria are blocking the lymphatics.
And what about for someone who's paralyzed? So you have someone who's a quadriplegic or something?
Yeah, well, basically, it's a good question. I've never really thought a lot about it, but they don't necessarily have enormous dependent swelling. But they're not walking, so they're not sort of pumping a lot of fluid out, I guess, also. Yeah, it's a good question. I mean, and of course, a lot of them, if you're bedridden, that's not a problem. But I guess I haven't thought about that a lot.
I wonder if this is
I'm
why...
not a medical doctor, you see. So.
Right. Well, I wonder if this is why when you're sitting at your desk for hours a day, whether that's
your ankles
added...
can swell. Your ankles can swell, yeah. Yeah, you need to get up and walk around. I mean, the best thing you can do for your health basically is move quite a bit. The more you can move. I mean, you don't need to be doing it all the time. I've been trying with standing desks and stuff, but I'm not sure that's all that great. But it's just don't sit for too long. Get up, move around a bit. Watching TV, even get up, walk around and watch the TV while you're standing up, and do get some reasonable steps every day and all that sort of thing. Yeah.
But so killer T cells, they will detect, they'll find a cell that
they're interacting with a cell. So as a physicist, think about this. I mean, there's a whole physics of this, biophysics of it. You've got a cell with multiple receptors, all the same. You also can have secondary receptors, which will also help bind T cells together. And then you've got a virus-infected cell, which is probably bigger than the lymphocyte, maybe not. And it's got lots of modified bits of transplant molecule on itself. So what you've got is a situation where you've got clusters of molecules bringing other clusters together. So you get these capping phenomena. You get coalescence. They come together into what the immunologists, I think, incorrectly call synapses. It's not really a synapse in the sense of a synapse in a nerve, but you'll get these sort of coming together. So, and we talk about affinity and avidity. I mean, the affinity of a molecule for another, for a protein, except a ligand interaction or whatever, there's that binding affinity. But then you've got a situation where you have multiple lower affinity molecules binding to other lower affinity binding, which we call avidity. So the interaction between the T cell and the virus-infected cell is actually an exercise in avidity, and there's a whole physics there, which I don't know if anyone's ever really tackled all that seriously, quite frankly.
About how the chemical interactions actually
that bonding really works when you've got these multiple interactions, and what the anyway, I'm not a biophysicist, but there is a field of biophysics, obviously.
But so the end effect is that these infected cells are being killed because they're the factories of the virus. So how much damage can actually be done by our own immune system to ourselves? I mean,
well, the same thing can happen if we react against ourselves. Paul Ehrlich, the great immunologist, he's talked of as the father of immunology. He won the Nobel Prize in about 1905 or something. He talked about horror autotoxicus. Okay. Yeah. Now, most autoimmune disease, though, is not our killer T cells killing ourselves. It's basically more what we call the helper T cell, which produces all sort of chemokines and cytokines and various molecules, and producing those molecules in, say, a joint, causing inflammation, other cells to come in. Inflammation causes swelling, swelling causes pain. Because so
arthritis.
Yeah, arthritis. You've got pain. All membranes have pain receptors in them. So if you distend membranes, you get pain. And swelling is the cause of a lot of pain. Yeah.
Is there a trade-off between how infectious a virus is and how dangerous it is to someone once they've caught the virus?
No, not necessarily. Some viruses are highly infectious, but they're not terribly pathogenic. So the current, I'd say COVID is really a highly infectious virus, but unless you're elderly, it's not terribly pathogenic in most people. The hooker is the long COVID thing for younger people, because younger people do get long COVID. And but you can, if you take the coronaviruses, the beta coronaviruses, before 2000, or the coronavirus, before 2000 there were 2 coronaviruses circulating in humans, both of which cause common colds and flu. And they're one of among 100 viruses that cause that sort of symptoms of all different types of viruses. And so after 2000, there are 5. Something has changed, and basically the original SARS virus, which came across from bats to a little animal called a civet cat to humans, basically in these live animal markets in China. That original SARS virus only infected, we know, it infected about 8,000 people, and about 10% of them died. Now, COVID, SARS-CoV-2, infinitely more infectious, but the real death rate, hard to know exactly, but probably more like 0.1 to 0.3%. So, you know, quite low, but very targeted towards people who've got compromised immune systems, which is usually, I mean, the compromise of age, for instance. There's another virus called MERS, Middle Eastern Respiratory Syncytial. Again, it goes from, we think, from bats to camels to humans. It kills about 30%, but it's not nearly as infectious. So I think, I'd thought for a long time that a highly infectious virus is highly lethal. That's Ebola. Ebola is, you know, a terrible disease, highly infectious, from body fluids. People in Africa early on often got it, and they still can happen, from the practice of if they die from what's called wet Ebola, they secrete a lot of this stuff, and then people kissing the corpse.
Okay.
And that was one of the ways that people got Ebola. Well, Ebola is so infectious and so lethal that people pick it up very quickly. So we haven't had an Ebola pandemic. And we probably won't have as long as we've got reasonable public health. But if you've got a virus like CoV-2, which infects large numbers of people, and with a lot of them, particularly younger people, doesn't make them particularly sick, so they're still moving around. This is an ideal mechanism for a virus to spread. All viruses want to do in nature is survive, spread, and replicate, and so forth. That's the whole evolutionary imperative. Okay, they don't want to kill us. Some of them do. I mean, rabies, one of the ways it transmits is it kills you, and then you're eaten by a dog that gets it or something.
But so there's nothing stopping a virus which has a long latency period, which is respiratory, but which also kills like Ebola.
Well, most, you know, they don't. COVID doesn't have a long latency period. It's an acute infection, and it's largely cleared. I think we worry that some of the long COVID people are people who haven't cleared the virus properly. They've still got persistent infection. I mean, latent viruses, we've got a whole lot of latent viruses in us. The herpes viruses, cold sores, Epstein-Barr virus, shingles. These are big viruses that go latent, but they don't change very much. And we've molded those viruses over the thousands of years, and they've molded us. You know, so our immune system, to some extent, reflects our interactions with viruses that are traditionally pathogens of us, particularly herpes viruses, I think.
But so people talk about the hope that eventually what we'll end up with is a coronavirus which is much less lethal and which just becomes like the common cold.
It could well be that it could be Omicron. There's a debate about whether Omicron is less lethal than the original strain. Some people say it's not much different. Others say it's much milder. Hard to know because now so many people have been infected or vaccinated or infected and vaccinated. So we don't know what the sort of resistance levels there are really, and the disease generally looks milder.
But what's the mechanism though for why would it be the case that a milder variation would dominate over time?
Well, if it spreads readily and it's not killing people. You know, killing people is a bad way to get spread with most viruses. With a respiratory pathogen, you want people walking around, coughing and spluttering and going to shopping malls. And so that's the ideal for spread. So you don't want to kill people. So, but viruses can evolve to be more virulent. I mean, it does happen. But generally, it's the hope is that they'll evolve to be less virulent, but to some extent that's hope. Because you know this virus is spreading very effectively. It kills old people and not killing young people on the whole, so it gets around quite nicely.
One of the key news stories going back some time now is this lab leak hypothesis. Is first of all, I just want to ask, when it comes to gain of function research, what are the reasons, the legitimate reasons why?
Well, the virologists have been trying to understand why these viruses kill us. So they've been playing around with the viruses to try and understand what it is that makes them virulent, what virulence really means in terms of the molecular structure of the virus, And if we could target that, if we could find out, maybe we could design a new therapy based on maybe mRNA, for instance, that would be a really novel therapy to stop. Or the other thing is, of course, if you're going to understand what it is about the virus that really makes it highly virulent, could you then, as you do surveillance to try and see what's out there, could you pick the viruses that are likely to be a real danger? And so they've been trying to understand this, and so some of that resulted in what was called gain of function experiments. And it became a very politicized area. And so everything was tightened up, and this sort of research, which was often going on at a somewhat lower level, then was then transferred into level 4 labs. I mean, these are labs where everyone's clad in a spacesuit. They've either got a oxygen on their back, and they're breathing through a tube, or they're connected by a tube and they're all negative pressure. And occasionally people get infected. I mean, things go wrong. Things always go wrong. I mean, they jab themselves in the finger through a glove or something like that. I don't know, actually. I mean, people think, you'd sort of think from what you read, these viruses are getting out of labs all the time. I mean, I don't know of any escape from a level 4 lab. I know some people have been infected by accident, but have they infected anyone else over the last 20 years? I mean, modern level 4 labs, I think it's very difficult to get a leak because anything goes wrong is immediately reported. But there's been some suspicions that the Chinese lab wasn't running properly and stuff. But there's no real evidence that it has leaked out of a lab. There's nothing in the sequence of the virus that the people who know these viruses say that tells us that it's been in a lab or that anyone's tried to manipulate it.
See, this is what I wanted to ask you about. If someone uses CRISPR or something like this on an organism, can you actually detect that organism?
I'm not so sure about CRISPR, but basically the sort of standard engineering techniques, the molecular virologists would pick those up. I'm not so sure. I mean, you'd really need to ask someone who's a molecular virologist. But the guys who know these viruses say there's nothing they're seeing in the virus sequence that's telling them that it's come out of a lab or that anyone's manipulated it. But you can't, I mean, it's almost impossible to say, well, maybe people who were doing virus surveillance brought this virus back to the lab and it got out of the lab. And it's almost impossible to say that didn't happen. But there's no particular reason to think it did. And there is sort of reasonably good evidence that it clustered around that seafood market in Wuhan and initially. But there's also evidence that there were 2 strains initially. Now if there were 2 strains right from the beginning, and it really did begin in humans in November, December 2019, it makes it very unlikely it came out of a lab. What would be much more likely is that the virus went into some second species, from bats, say, into raccoon dogs, one of these species which may be sort of bred in breeding colonies, say in Vietnam or somewhere, and then they sell these animals up into China. And so basically, if you had a virus established in a breeding colony of some other animal, and especially if it's not causing severe disease in those animals, but it's just evolving, you could start to see variants emerging within a breeding colony. So you could imagine that if animals are transported from a particular colony where this virus has been in for some time, you might see a couple of variants coming across into humans. So there's no particular reason to think it's come out of a lab. But a lot of people just like to believe this. I mean, firstly, it's anti-science. I mean, they're blaming the virologists, and secondly, they just don't like the sense that we're totally at the mercy of nature, which we are.
They would prefer to be at the mercy of a foreign power.
And we know, for instance, from the live bird markets, I mean, people get infected over and over and over with influenza viruses in live bird markets. It happens all the time. It's basically the cause of the H5N1 thing where people were killed, H7N9, happens all the time.
Then can I ask, in terms of ability, do we really have the ability to, from ground level, design and construct if someone wanted to...
If someone wanted to do it, I don't think they'd know how to do it, quite frankly. I mean, if you wanted to make a virus that was virulent in humans, I don't think that scientists would necessarily know how to do that. But what you would do is you would be a dictator with a large prison population. Mm-hmm. And what you would do is infect some of those prisoners, keep them all together, and then when some of them start to die, you would select the virus that's in the ones that are dying, and you would propagate that. So, you could do it. But I don't think people know enough about the basis of virus virulence to actually sit down. They could take a highly virulent avian virus in flu, say, and recombine it with a highly virulent, with a less virulent human virus. We worry that will happen in nature. That's always the concern. And the Hong Kong flu, the H3N2 Hong Kong flu that came across in 1968 is probably one of those. And it's possible the 1819 one, which was so terribly virulent, is one of those. It's a bird virus that reassociated with a human virus. The flu virus has got 8 different bits of its genome and it repackages. And of course the 2009 swine flu virus, 2 different swine viruses got together and came and created a virus which transmitted very well in humans, but wasn't particularly virulent.
So I don't know very much about how viruses propagate, but I didn't understand that you could get 2 viruses which, it sounds like sexual reproduction almost.
No, you'd have to actually get a single cell infected with 2 different flu viruses. Mm-hmm. You can do this in the lab all the time. It works with flu. Flu has its genetic material in 8 different segments. So if you take a cell culture and you infect cells with 2 different flu viruses, what you will get is they will reassociate in the cell. And you'll get a novel, it's called a recombinant, but it's actually a reassortment. But then you can also get viral recombination. You can get changes within the viral genome. You see a bit of that with COVID, I think, SARS-CoV-2. But that's one of the mechanisms for pandemic flu viruses coming across, we think.
I see.
We worry that someone with a human flu viruses will then get infected with a bird one, and some cells will have both viruses in them, and a new strain will come out of it.
And be highly virulent.
And be a pandemic strain, yeah.
But, okay, so when it comes to existential risk, how do you do you put pandemics above climate change? Like, how should we?
Well, it's different. And before COVID-2, I would have ranked pandemics much lower, quite frankly. But pandemics. I mean, this virus is not going to kill us out, obviously, but it may cause an enormous amount of economic damage, and it's causing, depending on how long COVID plays out, it's causing a lot of debility. So it's causing a lot of financial costs and a lot of social costs. Would we see a virus which is as infectious as this and kills 10% of people? I don't know. I think we would react much more strongly, of course, and maybe close it down a lot quicker. We don't know. And climate change, though, I mean, is this steady, inexorable progression. And that's the real problem with it is, I mean, we've seen how quickly people tire of taking remedial measures. What are we saying with climate change? We're saying, we may take your pickup truck away. I mean, that would be a terrible infringement, wouldn't it? I'm down at Point Lonsdale. Point Lonsdale is the port. All the ships that come in to Melbourne come past Point Lonsdale, in fact. So you see these massive container ships coming on, and you can see the enormous amount of, the dirtiest transport in the whole world, basically, is big ships. And what are they? There's all these containers, many are full of useless crap that people buy and throw away. I mean, so are you really going to get the whole world off the endless consumption of useless crap? That's what drives our economy, right?
I suppose that the thing that I worry about is when I look at the solutions to climate change, you often see that people fixate on solutions like, let's say, electric cars, which are very sexy. But if you compare them to public transport, if you were going to throw your eggs into a basket, then public transport probably beats out electric cars.
Absolutely. I mean, and there's a whole climate cost in making your electric car battery and your electric car. And then you've got to fuel that electric car. To my mind, to think that we're actually going to fuel modern society. I mean, for instance, if you have sort of self-driving cars, there's an enormous amount of computing required, an enormous amount of energy required to do that. There's an enormous amount of energy required for your electric car. You've got to charge it somehow. So maybe in Australia, where you can put solar panels on every house and so forth, but then the sun doesn't always shine. And so I think we're vastly underestimating the energy requirements for the future, and the thought that we can do it solely from renewables, I'd really like to see some very good mathematical studies of this. It's like saying gas is clean, but you can never find data on the gas leak. 20% of some of the gas fields, 20% of the gas that comes off is straight CO2, which is vented straight into the atmosphere. That's not clean. There's a methane leak from improperly attended wellheads and boreholes. That's not clean. Methane's a worse greenhouse gas than carbon dioxide. Then, of course, if you're going to export your methane, you've got to liquefy it. You've got to use energy to do that. So, I'm not convinced that gas is any cleaner than coal. In fact, coal may be preferable because it sends up a lot of soot and makes people sick. So people are at least aware it's there.
Can I ask then, so do you think in some sense COVID was like a trial run or a, it was bad, but do you think in the end it's going to have some protective effect against whatever the next pandemic is?
If we're intelligent, it will, but I'm not too sure about our capacity to learn. I think the professionals will learn from it, but will we really learn the lessons we need to learn from it? I mean, the lesson for Australia is always, on anything, break down the silos. But we're so good at silos. Yeah, and I think the symbol on the Qantas jet tail shouldn't be a kangaroo; it should be a silo.
How serious is the threat of antimicrobial resistance then?
It's very serious. I mean, bacterial resistance, antimicrobial resistance. Basically, the drug companies, pharmaceutical companies, they're all for profit operations, and they back right off on antibiotic research because there wasn't enough money in it. And so people like Gates Foundation have come in and they've tried to fill that gap, but there's not enough antibiotic. There's not a big enough pipeline. And we need to be looking to some different types of antibiotic type mechanisms. And so it's one that worries my colleagues a lot who are in, and it's an increasing problem in hospitalised people.
So in terms of impact, the impact of your research on medicine, what sort of therapies do we have access to today?
Well, it was a basic discovery which told us about how, one half of the immune system basically works by focusing on our own cells through the transplant molecules. So that was a massive breakthrough in understanding. That's why we got a Nobel Prize. We didn't work it all out. I mean, we made the initial discovery, and then other people helped and did various things which were absolutely central. I mean, that's how you get a Nobel Prize. You make the initial discovery, a lot of other people do the work, and you get the Nobel Prize. But basically, it's the new cancer therapies, the immune, the ones that sort of turn T cells back on in tumours and so forth. They come through a lineage from what we did, but actually what we actually did hasn't sort of led to a major therapy, if you like. It's led to an understanding of the cellular immune response.
But so you can't put your thumb down on, for example,
no, it's not like developing a drug and say,
okay,
this drug, we worked out why this person's getting cancer and this molecule has changed. We've designed this drug to block that molecule, and there you go. So that's not the sort of, and what Nobel Prizes would award is the first time that's done. But then maybe another 100 people who do that with different cancers, and they won't get Nobel Prizes.
Do you think eventually, first off, why is it that cancers can evade our current system? And do you think eventually we're going to have vaccines for cancers?
There may be a role for vaccines for cancers. People have been trying this a lot. The big breakthrough in cancer therapy There have been several. One is monoclonal antibodies made against particular molecules in the cancer, which can actually block the cancer. And some of the lymphomas and so forth have been very well treated with these. There have been some forms of breast cancer that have been quite well treated with them. So that was a direct therapy, but using a biological entity, basically antibodies that are cloned out, and you make these monoclonals. But then the other big breakthrough, and this was a Nobel Prize to Jim Allison and Takushi Honjo, is basically the recognition that there are immune checkpoint inhibitors. That we knew for many, many years that tumours would often have immune killer T cells sitting in them that were doing nothing. The tumour had turned them off. And basically Jim discovered how to turn them back on again by blocking these checkpoint molecules. And so then these T cells turn on and they kill off the tumour. So that was a big breakthrough, initially with melanoma, then with a number of other tumours. Now, the hope is that with some tumours that doesn't work at all, but there's a hope that if you could actually create that killer T cell response by using an appropriate vaccine, and mRNA may be just the way to do it actually, that you could actually tailor individual killer T cell responses, or even make killer T cell responses that could be used on a lot of different individuals, that would then, even if those cells were turned off, the checkpoint things would turn them back on again. So there may be a whole new era of vaccine immunity, which is perhaps tailored, well, certainly tailored to a particular tumour, but it might actually need to be tailored to a particular individual.
So personalised medicine.
Yeah, personalised medicine, which makes it enormously expensive. And that's the problem with modern medicine. These monoclonal antibody therapies are enormously expensive. And
what about in terms of anti-rejection medications or therapies? Do you think at some point we're going to, say for example you wanted to have a kidney transplant, can we also transplant, say, a part of the immune system of the donor, or are there...
Well, we could. I mean, you could take the individual and do a bone marrow reconstitution if they're reasonably matched. But, that can work. But basically that's not usually what happens. I mean, a bone marrow transplant is a hell of a process, it's not something trivial. And so, but a lot of graft rejection has been actually using an immunosuppressive drug that's worked very well, and so transplants work a lot. But people are on therapy for the rest of their life.
One of the reasons why I asked whether our immune system is localized, going back to the autoimmune response.
Well, the responses, initial responses are localized response, but then it generalizes and the cells are everywhere.
I had sort of hoped that if you had a transplant, maybe you could
cut off that arm or something.
No. But I just mean apply the anti-rejection drugs locally. Or
no, it doesn't. I mean, if you could, a lot of the problem with therapy is access of the therapeutic entity and targeting of the therapeutic entity, and that's really a lot of the problem. I mean, we flood the body with drug, whereas you only really need it at, say, some particular location. But you have to flood the body unless you're going to, there's no way you can actually deliver it specifically to that location. And there's a lot of thinking about how you might do that. But I don't think any significant drugs that have come along that have actually achieved it yet. So, there's a whole lot of stuff that needs to be done in science, and massive possibilities. But and we'd like, there are some things we'd really like to see. I mean, too many young women still die of cancer, for instance.
Breast cancer specifically, or
breast cancer, ovarian cancer. Yeah.
Do women have a higher incidence of cancer than men?
I'm not sure.
Or is it an age thing? Because I know that prostate cancer, there's a high incidence, but it's usually
older men.
It's
older men usually. Not always older men, but it tends to be older men. Yeah. And prostate cancer still kills people. And but it, particularly young mothers and so forth dying of breast cancer, ovarian cancer particularly. Cervical cancer, the vaccine now is hopefully everyone gets it. Yeah, that helps a lot. I mean, it's a papillomavirus-induced thing. Yeah.
But so, since you said your research that you got the Nobel for was more fundamental in nature, when you initially, I think it's 50 or so years ago now that you had
The actual discovery was made 50 years ago next year.
And so
this year, 50 years ago this year.
Well, congratulations.
Yeah.
But so when you initially had the discovery, what was the reaction? Was it something where you really had to fight for recognition, or was it something that people really accepted?
Actually, it was. It was. We saw it and we said, "God, I'm out of here. This is something," and it was basically unexpected, totally unexpected. And we saw the immune response linking to the transplant molecules. So, and we worked that out fairly quickly using various genetically bred mice that had been bred to study graft rejection, actually. So we did that. And we reported this, and people were very interested. It was the first time anyone had said, this is a role for the transplant system, and this is basically how that sort of type of response is working. But the explanation we had, a lot of people didn't accept. We said that the virus was altering the transplant molecule. We called it altered self. It turns out it's actually it's a peptide from the virus binding to the transplant molecule, but that it is altered self. So that took about 10 years to discover, actually, and it was someone else who finally worked that out. But so the phenomenon was recognised, and we became sort of famous overnight. But really, the explanation wasn't generally accepted for about another 10 years, and it took. It was 22 years after we published our first papers, we got the Nobel Prize. That's not unusual. I mean, it's often 20, 25, 30 years even to get a Nobel Prize. I mean, they don't like to get it wrong. Yeah.
On the topic of the Nobel, what role do you think ego plays in science? Do you think, for instance, do you ever think about how am I going to be remembered 100 years from now or 1,000 years from now?
Well, most scientists have forgotten very quickly. I mean, we remember a few. Einstein for his hair, and E equals mc squared. Even if you don't know what it means, people remember it. But most scientists are quickly forgotten. I mean, we still rattle on about Newton and stuff. And physicists, because the God particle. I mean, that's very memorable and so forth. But basically, a lot of the historians of science all focus on physics. They don't focus on biology because biology tells them something very uncomfortable.
There's Darwin.
Yeah, Darwin, but biology tells them something very uncomfortable. Because it tells us basically we don't know most of the time what the hell's going on, and a lot of discoveries made by pure chance. And that's not very good for a philosopher of science. They don't really like that very much. And
there's a lot of chance in physics too.
Yeah, but you can put it in nice physical terms. Yeah,
I think that comes afterwards when you're writing the paper.
Yeah,
right.
Yeah.
You don't.
Oh yeah, no. It's all. I mean, the scientific paper is basically fraud. I mean, you never write in the sense that the introduction as to why you actually did the experiment. You might discuss in the discussion why you actually did it, but the introduction is really you never write the introduction till you've written the results, the discussion, and the conclusions. And then you can write the introduction, which leads into why you would get those particular results.
You had incredible foresight.
Because otherwise you're never going to get your paper accepted, because if you really put in the introduction why we did these experiments, you put up so many red flags to a reviewer that you never get it accepted.
And of course we don't really have journals for failed experiments, which is another problem.
No. Well, you do now. You can publish absolutely anything somewhere.
They're starting to develop. Anyway, this is something.
I think the way physics handles it's very good, actually. That you basically, I mean, as I understand it, a lot of physics, theoretical physics at least, means you circulate the paper before
on the archive,
and then people discuss it, and the actual scientific paper is often a synthesis of the criticisms and so forth that have come through, and then you get a very. But that hasn't been the case with biomedicine. But it's been a bit with these preprints. It's been happening a bit now with COVID, for instance, that you're getting that effect. It probably wouldn't work in biomedicine. And there's, I think, biomedicine particularly is a complicated culture because it has the doctors in it too. I mean, you have professional scientists like me who really just do science. But then you have a lot of doctors who are sort of sometimes maybe a bit more ego-driven and so forth, that, and often doing science somewhat third hand too, which is somewhat of a concern.
But I think that the meaning behind my question was more, do you think ego is useful in propagating, in pushing science forward? Because we name equations after people, and you have a building named after you. And
that's not my choice. I mean, they asked me if they could use my name, and I said, well, why don't you go out and raise a lot of money and get it from some wealthy guy and name the building after them? And they said, well, that doesn't work that here. And so they did name the building after me, but usually buildings are named after people after they're dead. But, so it was unusual. And I've always told them, if you can sell the building name off for $50 million, go ahead and do it. Yeah. But no, I don't think. I mean, you don't do science to become famous. You do science because you're engaged. You want to understand what's going on at a basic level. You want to understand what's going on. If you can do something that's useful, great. But that's not really the primary motivation of the type of science that leads to discovery. I mean, that's basically curiosity-driven research. But you've got scientists operating at every level. I mean, you've got, in the drug industry, for instance, you've got scientists who are developing a product and so forth. It's all perfectly legitimate, but these people don't win Nobel Prizes.
Then what about the superstars, so the Darwins and the Einsteins? Do you think they'll be forgotten as well?
Darwin is fixed in the firmament, basically.
But let's go forward 10,000 years or something. We're all robots or whatever.
I don't know. Yeah. I mean, but evolution. I mean, natural selection was a very big idea. And Alfred Russel Wallace. Wallace got the same idea at the same time from his studies in what he was doing. He was trapping animals in Indonesia, really, and selling them. So, but that's one of the big ideas. I mean, if with biology, if it doesn't fit with evolution, it's probably wrong. Yeah.
So you mentioned Wallace, and so he isn't remembered the same way that Darwin is. And you often hear stories about people saying, so-and-so deserved the Nobel Prize, but for whatever reason they weren't recognized and so on. As someone who has won the Nobel Prize, how should we conceptualize these stories about?
They give, if you're talking about a Nobel Prize in the sciences, they give it to 3 people max. Okay, so it was fairly straightforward with our Nobel Prize. I thought there was another guy they could have included who sort of discovered the peptide thing, but they didn't. They chose not to. They always go back to the original discovery. So, and so Mendel, of course, he's before the Nobel Prize, as is Darwin, and but in many cases, now it's a team. And a lot of the angst about Nobel Prizes, sometimes people feel they've been unjustifiably left out. And the other problem, though, is where you've had a team, and it's the postdoc who makes the discovery, and then it's the professor who gets the prize. That they're tending more now to actually recognise the postdoc. But early on, there were some cases that were fairly egregious, I think, where it was the young person who really made the discovery and pushed it, and then the professor who sort of took the credit for it. I think that happens a lot less now. And you commonly now see a senior and a junior person associated with a number of them.
Although to be fair, quite often the senior person has 10 different projects that they could be working on. They understand each one of them. It's just a time
sure. And they provide the resources and the environment, and they may have provided a lot of the work that sort of preceded this breakthrough and so forth. So it depends, how independent that is. But there can be some real anguish around those issues.
I think also.
There's one I know of where people say, well, X got the Nobel Prize, but he really didn't do anything. We were just in his lab and working with him, and we finally convinced him, and then he gets the Nobel Prize. That can happen.
Although people like to see their impact as being they're watching. They watch every step of the way of their own work, but they don't see what's going on in the background. And so,
but it is problematic, and the Swedes worry about it. Because they know that science is not done. I mean, our discovery was done in a small lab thing. It was just a couple of young guys working together. An extraordinary situation. Now we'd be working for some famous guy at that stage of our career, and that wasn't the way it was. It was just two young guys, and but that's now very unusual. And usually you've got big teams, and a small lab now is often 8 or 10 people at least. Yeah.
So I want to jump back, just it's sort of on topic, back to science and politics a little bit, and I'm wondering, when it comes to science funding, right? How can we be sure? How can we ensure that there's an effective distribution of funds? Because what I tend to see in physics, at least, is that you get these very popular fields, or you get some things that are fashionable. So for example, it was supersymmetry, then it was string theory, and right now you might say it's quantum computing and gravitational waves. And what happens is you have big guys in these fields that then are making decisions about where the money's going. And how can we ensure that, so for someone like yourself,
it's difficult, and the cultures are different too. I mean, a lot of the funding we see for particularly, say, experimental physics, these are big budget items that really, they're political decisions in the end. Whereas the type of money that comes into biomedical research traditionally has been reviewed through grants that are quite small, investigator initiated and all the rest of it. And it can be a difficult sell to government. I mean, some people in the government of Australia say, well, why do we do science? We're not really, And basically, if we want to be players, we have to do it. How much we actually earn from it. I mean, it's said that biomedical research actually brings a lot of money into Australia, and there are people who have various calculations out there. I'm not up on this stuff anymore. I was sort of playing that game and trying to talk to politicians for a long time, but I sort of came to the end of it. But when you decide to sort of the big array telescope, for instance, this is a political decision in the end. It's a prestige decision. And it's made at the political level. So you hand out hundreds of millions of dollars much more easily than you hand out $1 million, where you've got all this peer review going on through various committees and stuff.
Well, if you just
and then and also if you're putting out research money in the United States. All that money gets spent in the United States. The reagents are bought in the United States. The equipment is bought in the United States. The people are employed there, and the benefit goes there. But if you're doing that in Australia, you're buying stuff from the United States, and so not all that money gets spent in within country, so to speak.
For the Square Kilometre Array Telescope, I think if you're just interested in the science, then Australia was the correct place for it to be,
sure.
rather than South Africa. But that's a completely different topic.
Yeah.
Let me ask then. So, how should you, if you were the Prime Minister, Peter Doherty, or whoever's in charge of these funding decisions, how do you decide the breakup between fundamental research, like what you were doing, or sort of more applied?
I think all governments, people who are running governments and so forth, have a perfect right to say, we want you to look at these particular problems. We need them. But the problem with that is, particularly in biomedicine, you get what's called the disease of the month club. So I think the politicians have to decide that an activity is worthwhile to give it a reasonable level of funding, and then let it run with the professionals running it, really. I mean, if you pour all the money into diabetes, for instance, you'll fund a lot of people who are not very good, and you'll fund a lot of other people in another area who are very good, and you won't fund them at all. So, you have to leave it up. But it's a difficult area for government, because you're putting out a fairly significant amount of government funding on a sort of speculative basis, if you like, or to keep a culture running, or to keep a high level of intellectual activity in your country, so to speak. So it's not a straightforward thing. It's not like putting out money to build a building or build a bridge or something like that. So I think you need a reasonable level of sophistication at the level of government. I think we've certainly got that probably more on the Labor side of politics here than the previous Liberal government, which was not terribly sophisticated. But for instance, John Howard, a very conservative Prime Minister, very interested in medical research, and I think he doubled the budget twice. And saw the value of it. because it is a value based in excellence and hard work and genuine innovation and stuff. So it does give a flavour to a society.
So, two more sort of political questions. How do we ensure, most research is done in universities, there are also institutions, but how do you ensure that universities act to the benefit or in the interests of the students and society, rather, because they're businesses as well, rather than in their own interests? I can give you examples if you'd like.
Yeah, I'm not terribly up on, even though I work in a university, I involve myself in university politics and administration as little as possible. But basically, I think it's if you're going to give money to institutions to hand out, I mean Max Planck, for instance, then you have to have really good rules and really high quality people running it. And you'll see with the Max Planck, I mean, you've worked in that system, and it's certainly a great system for the scientists. But they're very, very difficult for people to advance within that system, as you know, and so I think for biomedicine, what works is the investigator-initiated research project. And that means basically universities have just got to people who are competitive and smart if they want to get resources from it. And of course in American universities there's a very big pressure to do that, because not only do the investigators bring in their research funds, they bring in indirect costs. So, for instance, when I was working in a place called the Wistow Institute in Philadelphia, which is a private biomedical research institute embedded in the University of Pennsylvania, but not controlled by it. And Penn's one of the Ivy schools. And in medicine, Penn is very prominent. And so, basically, every $100,000 I got in grant money, the institute got $100,000 in indirect costs that came to the institution. So that's a really good incentive to employ people who can actually generate grant funding. And that's a blunt instrument, because not all the people, some people are just better at grants actually than the science, but there is a correlation obviously. So but we don't have that indirect cost mechanism here. But on the whole, it's universities, if they want to be competitive, have to employ the brightest people. That's basically it. Now, how that translates to teaching is another matter again. I mean, actually, not necessarily. I mean, some of the best teaching institutions in the United States aren't the research universities, they're the liberal arts colleges.
So one example I'm personally interested in is if you look at, for example, the length of junior contracts.
Yeah.
So for the state that's funding a university, it might be interesting to have a very long contract, say 5 years, so that you bring someone in, they become embedded in the system, and they eventually might even stay, even if they don't stay in research. Whereas for the university, maybe it's good to have shorter 2-year periods. And
no, I think for everyone it's better to have, once you're getting someone on the road to running their own research group, at a junior level, I think you really need 5-year commitments, 7-year commitments, and so forth. I mean, I've worked in universities where I've had tenured positions, tenured for life, and given them up because they were ridiculous. The Australian National University.
Ridiculous in what sense? Sorry.
Well, because you ended up with an enormous deadwood problem, basically. If you tenure people for life, never review them, and you just hand them money, you'll end up with it just,
doing nothing.
Well, they don't do nothing, but they do stuff that they were doing 30 years ago.
So what's the sweet spot then?
You need a well-funded system. But St Jude Children's Hospital, where I worked in the United States, nobody was permanent. As a department head, I served at the pleasure of the board, but everyone was on 5 or 3-year contracts. Once you got up to associate professor, you're on a 5-year contract, 5-year renewable. And if they were going to terminate, you got 2 years' notice. So I think in a research institute, a research-only institution, you need renewable contracts, and you need to give people a transition. But people tend to get the message when they're not doing well, and they'll look for a job in a university. But what's happened with American universities, where there's no retirement age, I mean, a lot of them are clogged up with people who just won't go. I mean, you know, there's a lot of dead wood. And I mean, tenure at Johns Hopkins University means if you're not funding your salary and your research through grants, your salary will be cut 10% a year every year until you get refunded. Okay, I mean, there's that sort of mechanism, which is really brutal. Yeah, but to work in science, do science full time, funded from the public sector, I mean, it's an immense privilege actually. And basically, you can't have it filled up with people who are not doing a good job.
And so, one of the issues, so at the moment where what's big in research is the discussion about, for example, minority groups or women in physics or women in science, STEM. And how do you think, not just for these groups, but in general, how do you protect junior researchers during, for example, childbearing years and when they're having families?
Well, we did it. I mean, locally, we had some big grants, and basically, the younger women who are running research labs, when they needed to take that time out, we kept the labs running. And they were able to do that part time and keep things running. I mean, that can be a sort of a positive feature of an umbrella type thing. If someone is I don't think it's possible now to do effective science completely alone, so to speak. So it's difficult. I mean, it's a complex situation, obviously. Certainly having really good child minding within the institution is great. I mean, the Hall Institute, for instance, Doug Hilton, I think, set up an actual creche within the institution and preschool and looking after kids within the institution, which has been a big help for women. But also, as you know, there are many situations now where it's not the woman who's taking, if she's the really talented one, and it's a husband-wife combination, it's the guy who's taking the childcare role. And that's happening in science, it's happening in business and all sorts of situations. We know a number of cases where that's so. So one partner is stepping back, but not necessarily the woman. But of course, obviously, the woman has to have the kid. So, yeah. So, yeah, I think there's a lot of sensitivity to that, and it's not my sort of thing. But my own personal experience is we did everything possible to help young women who were talented, and were going through that those years of small children and so forth, and it worked fine. I mean.
I want to end the discussion with a few questions that are sort of focused towards the future, and also which will sort of flesh out a bit to do with your personality. And so I've just got a few questions along those lines. Do you find it is ever hard to live up to your Nobel work, or to live up to the image of a laureate?
Honestly, I don't care about any of it. I really don't care. I never have cared very much what other people think of me. I basically do what interests me. Now, that's kind of selfish in a way. I do what interests me. I don't get involved in races, and I don't follow fashion. Never done it. Always been bored by it. But you know, particularly with American science, it often, particularly in the 80s, 70s, 80s, 60s, 70s, it was like a swarm of bees. I mean, they'd all be swarmed here. Then someone would discover something over there. They'd all swarm over there, and they'd bzzz, and then they'd all do the same stuff. And then something would happen over here. They'd all swarm over here. I just stayed there and kept doing what I was doing and asking the questions that interested me. I just don't care about it. And a lot of the sort of attention with the Nobel, it's fine. I'd handle it okay, but it can be somewhat nauseating at times.
Sycophants and...
Well, sycophancy is always nauseating. I just can't stand it, actually. You know, for instance, sometimes you get upgraded to first class on aeroplanes and they start to treat you the way they treat these wealthy businessmen. I find it quite unpleasant. I don't want these people hovering over me. Yeah. But of course, there's a whole culture that demands this. But I think they're basically creeps, and you know.
It's a little bit like, I've been trying to think about a good analogy. For soldiers we have statues, and we have war memorials, and we have things like this. And I suppose, I'm not saying there's some grand conspiracy, but these things do serve a purpose in society, right?
For pigeons, they certainly do.
For pigeons, they do, but also
a lot of the statues are being pulled down. So the statues of the Southern generals and so forth are all being pulled down. And people are saying, well, why are all these statues of men up there and there are no statues of women? There are a lot of women there should be statues too. I think this whole thing is, it's public, but I think public art doesn't need to be statues of people. And, being remembered. You do things because you want to do them. You don't do it to be remembered and so forth. So, I've written books. Is anyone going to read any of those books? Does anybody read them anyway? But, in the future, does it mean anything? Yeah. Shakespeare, fine. Jane Austen.
Well, I meant more along the lines of there's a function of these things in society, right? They do serve a purpose to get people to move in a certain way or to think in a certain way. There's a certain window of thought.
I think the idea of public service, great public service, you perpetuate in the sense of people like Martin Luther King, for instance. That's important. But basically, and you want people to identify with good positive sorts of goals, but it's a very confusing world at the moment. Religion, which did a lot of that. Religion did a lot of things that are not so good, as we all know, but it also, a lot of the service to people came through that dedication. And we're in this enormous transition phase, and everything being greatly confused now or changing very rapidly because of social media, which is an enormously powerful force, and the internet. Writing a book now, you can do the research from a lot of the research from your living room. Just when I wrote this book about, this is not an area I know about, war, for instance. But you can get all sorts of material just online that you could never find in a library, actually, unless you went to the National Library. A lot of the books, for instance, that were written about World War II, long out of print. Many of them have actually been digitized, and you can get them out of digital libraries easily. Quite extraordinary.
So, back to your research, what do you think the biggest open challenges are in immunization research, and what are you most excited to see being achieved?
Well, I think it's not. We can make products and we can make vaccines and so forth, but particularly COVID will have actually advanced this quite a bit. Our understanding of the human immune system is not great. When I tell a story about how an immune response works, what I'm doing is actually saying, well, we know this bit from the vaccine works in people, but a lot of the studies are actually in mice. So the actual conceptual basis of what I'm saying is largely based on experiments in mice. Now, through COVID, we've actually got a lot more information about human immune responses. Particularly, some areas of human immune response are very poorly studied. You would think kids would be fantastically well studied for immunity. They're not. Why? Because you can't go around sticking needles into kids all the time. And you can't go around sticking needles into babies and taking 10 or 20 mils of blood all the time. And so, it's complex. So you tend to study things when they go wrong, but there you have to be careful. Traditionally, human immunology was done very seriously by rheumatologists, autoimmune disease and all the rest of it, and neurologists, diseases like multiple sclerosis. So they were often very interested. The doctors were very interested in immunology. But there's a whole lot of other areas of medicine where people weren't interested in immunology at all. Only recently, cancer people got really interested in immunology with these new therapies. The gerontology community, never been very interested in immunology, though what kills a lot of people is actually failing immune systems. So a lot of this is now being done much better. in people. And I think that's a big advance. And we'll get a better understanding of the actual human immune response. I mean, mice are great to tell you about basic mechanisms, but as they say from the HIV world, mice lie and monkeys don't always tell the truth. And so I think that's one of the things that is happening. We're just getting a much better understanding of the human immune system.
What do you wish people understood? If there was one thing that you could get people to understand about science in general and immunology specifically, what would that be?
I think, scientists are not priests. We are not going to give you dogmatic information that said, this is how it is, this is absolutely how it is, go away and do this, okay? We're not priests. We're not working from belief, we're not working from conviction, we're working from evidence and ideas, and that changes. So what the scientist says is not, and what people hear is from a scientist when they talk is, this is the way it is. What the scientist is saying is our best understanding is that. That's all we say. Our best understanding is that.
What do you find beautiful about the world today, and what do you think young people should be excited about?
I think there's one really major issue that we have to tackle, and it's all linked, okay, and that's basically the issue we have to solve is what are we going to do about climate change? Because if we don't do that, I don't see humanity's got a whole lot of future, quite frankly. Would you agree, as a physicist?
Well, if we go 2 degrees up in warming, then that's bad, right, in the next 100 years?
Well, we're definitely going to go up 2 degrees, I think. I don't think there's any way we're not going to, quite frankly. But if we go up 3 degrees or 4 degrees, okay, I mean, we're finished, I mean, as far as I'm concerned. So that's the major issue. But there are all sorts of issues here. I mean, the issue of equity between people. And so if we don't solve that problem, if we don't achieve a greater level of equity, how do we progress this? If political leaders and big money divides people against each other, I mean, so we've got some massive social issues that have to be solved, and we've got really some very bad people out there with immense power, and you can name them, but really, what do you do about this? I mean, basically, the world is being run by greed.
But so if you had your time again...
Greed is not good. I mean, that's what Reagan and Thatcher justified. Greed is good. But, I mean, if you just have greed as a motive, you're just headed for destruction.
But so then, are you more worried today than you were, say, 50 years ago?
Oh, absolutely, yeah. I don't think any of us thought 50 years ago that, humanity would come to an end within the foreseeable. I mean, we were thinking that the world's getting better.
Mm-hmm.
I'm not convinced the world is getting better anymore. I mean, we're seeing democracies fail. We're seeing countries that are democratic electing to go authoritarian. It may be happening in Israel right now.
But so you lived through for example, Cuban Missile Crisis, and so the nuclear scare. There was the hole in the ozone layer. There were all sorts of issues that...
Yes, I mean, if we'd had a nuclear war, obviously, that would have been catastrophic. Though I don't think people had a real understanding of just how catastrophic that would be. But basically, I mean, we had a nuclear peace. It's only now that Putin is actually using that, using the fact that they have nuclear weapons to do what they're doing in Ukraine, I mean, which is pretty appalling. But then, the US has done appalling things too, and the invasion of Iraq, which totally destabilized the Middle East, was an exercise in insanity. I mean, Vietnam, crazy stuff.
Do you think then, if you had your time again, you're 30 years old, you're 25 years old, you'd skip the whole science thing and you'd go into...
I have no idea what I'd do if I was 25, 30 years old. I think I'd try and understand why human beings are as crazy as they are, but maybe psychiatry.
Well, Peter Doherty, it's been an absolute pleasure. Thank you very much for coming on the podcast. So in this interview, we haven't gone very in-depth into your research.
No.
It's
well, there's no point. I mean, this is work that was done 50 years ago, and
Well,
You know, I
we
mean,
also,
but it's complex and it's specific.
Mhm.
Basically a lot of things. In physics you have these big theories and stuff, but a lot of because of evolution, a lot of biology is specific to a particular system, and so that makes it less of a general point. I mean, that's why we're still making all these discoveries in biology, because evolution has taken us down paths that you wouldn't design. Yeah, it's not we're not designed, we're not engineered. Yeah.
So the thing that I struggle with so this is off topic for me. The sort of questions that I struggle with, because I of course, no, you can leave it on for now. I might cut in afterwards, but so the sorts of questions that I struggle with. So I as I said, I did some research into your background. I did some research into the way the immune system works. But what I hate doing is finding out some fact and then just asking the question to get you to regurgitate that fact.
Yeah, it's really boring.
It's really boring.
And I really hate people hate that. I don't want to talk about it. I've talked about it I've been talking about this stuff for decades, and I'm really bored by the whole thing, actually. And it's I'm interested. I'm very interested to see what we'll sort of unpick with COVID, because I think it's really thrown some. There are phenomena out there that we've kind of known about and largely ignored. I mean, a lot of our thinking about COVID was based on our experience with influenza. And when you get a vaccine, you've sort of solved the problem pretty well. But that's not what's happening with COVID. But you never get infected again with the same influenza virus in a way that would cause disease. Okay? You're always immune. But kids get infected with the same para-influenza virus year after year, little kids, and it doesn't change. It's just they have a milder infection each successive year. Then, when they bring that infection home, their parents who had that infection as kids catch it again.
Right.
And then Granny, who's had it all through, can kill her in the nursing home.
Yeah.
So we've never really dealt with this sort of partial immunity thing properly. And now also with this long COVID, we've got a whole new sort of ball game about what's going on here. We've had this thing about chronic fatigue syndrome for decades. And people have been very debilitated after virus infections or other events. Nobody's known why, and it's never been worked out, because you don't see a lot. But now we've got all these cases of long COVID, so hopefully this will be unpicked, and we'll sort of start to solve some of these problems, because people have been suffering, and they haven't been getting a lot of help, actually.
The two things that I'm really curious about is, first of all, okay, so we went into lockdown. We vaccinated against COVID, and we separated ourselves. We had all these restrictions put in place. I want to know what the impact is on the other respiratory diseases that sort of in parallel got affected by all these policies.
Well, I think we'll develop a better understanding of some of these diseases. But basically we had with everything locked down, we locked out flu. I mean, it had always been said you can't stop flu by stopping the planes. Well, you can. We locked it out. And we had all these lockdowns, we had all these other infections were at very low level. And then, of course, when everything relaxed, they came roaring back. So the US, and to some extent here, but much more in the US, has had a terrible problem with a virus called respiratory syncytial virus, which is a virus of babies, but basically it kills old people. And it's been putting a lot of older people in hospital and making them very sick. We may be just at the point of getting a decent vaccine for it, but we've had a friend in the US who's almost died of it. Our next door neighbour almost died of it. Doctor. And so it's locking down for COVID showed us certain things. It created a lot of mental health issues, particularly school kids, for instance.
And of course, at the end of the day, it would be very interesting to pick apart the statistics and see, we went through lockdowns and we didn't have as many deaths due to COVID, but maybe the rate of suicides went up, or maybe,
No, I think if you look at excess deaths for Australia, we've done really well, but because that would come up in your excess death statistics. But I think the mental health issues that came out of it may be a real issue. We had 2 of our grandchildren in college through this. I mean, their experience of college was greatly diminished. Really sad, actually. And so I think, there's we could learn a lot from it, and I hope we do. And I think that will affect the way we respond in the future. Yeah. And a lot of the objections that were raised and so on, they have some real validity in them, and we should look at that whole thing, and I hope that will influence us in the way we do these things in the future.
Of course, the other interesting,
because I think we'll have more of these events. I mean, the fact that 2 of those viruses were circulating before 2000, now there are 5, says to me, what's changed there? Well, international air travel, but we were having a lot of international air travel for 2000. What's happened is prosperity in China and Asia. And these are the countries that have live animal and live bird markets.
I mean, the other interesting question, of course, along these lines
and
is...
tourism to those areas is massively ramped up.
So the global response to the pandemic was... There were some brilliant things that happened, but on the other side, you saw, for example, masks and vaccines being stolen from various nations by other nations. You saw... You saw...
well, the first world nations definitely looked after each other, after themselves first, and that whole issue of equity is a massive issue. I mean, we're seeing this increasing with automation and all the rest of it. We're seeing this increasing concentration of wealth in fewer and fewer hands. I think it's a massive problem. I don't know how you handle it. The French Revolution, you handle it by guillotining people, but basically, how do you have a revolution when it's a global issue, not a local issue? You may have a revolution in a country, but a global revolution? I mean, I just don't think that happens.
And then on the other side, there was when lockdowns were being put in place, on national borders. So when national borders were shutting, and you were having people in the media calling this a racist response and so on. At some point, if we're going to have a global response, and these sort of lockdowns are going to have to be organised in an...
Well, you've got all sorts of things happening in that front. I mean, you've got this tremendous emigration out from areas of conflict or despair, and this is just going to get worse with climate change. As people starve, they'll do anything to get away from it. This theory. I mean, Tom Friedman has pushed the idea that the Arab Spring really resulted from very bad harvests, and what happened in Syria has also resulted from people. In fact, people were starving, and the government wouldn't do anything to help them. And this is related to climate change. So, we're going to get these enormous tensions, and then people in Europe say, reacting to the idea that their society is being destroyed by this influx of people who think differently and look differently. We sort of deplore these things, but there's a reality there too, and it's a very difficult. I think we're getting into an increasingly difficult world and a very challenged world.
I really wanted to end the podcast on a what do you find exciting about the world? What do you think young people should look forward to? I wanted to end it on a positive.
I think there's some enormously exciting things happening, but a lot of the exciting things that happen actually destroy more jobs and take people. There's so many
automation.
So much of what's happened is it's not that there aren't jobs, but it's the jobs that were good jobs have gone, and the jobs that people identified with for life. I mean, you think of the sort of tribes that people form into. I mean, it's all now around things like football and so forth. But there used to also be, there was a tribe around your workplace. Yeah, you worked for a firm for years. There was they often had, so if you look at the British industry, for instance, they had their own band concert thing. They had their own football team. There was a whole tribe around that.
Of course, today you move jobs every 5 years or 2 years or wherever you're.
Yeah. But those because those jobs don't exist anymore, the tribes don't exist anymore.
We have tribes that are online, right? You have these echo chambers.
Yeah, you have those tribes, but it's not the same. You're not getting together with them. You're not going to a picnic with them. You know, your Facebook friends don't come to your funeral. Well, maybe they do online.
Yeah, I mean, there have been online funerals for sure.
Oh, yeah, we've been attending a lot of online funerals.
Sadly through COVID, but I mean, in online
well,
gaming.
we're that age, you know, people are dying off all the time.